Alright, welcome back to Physics Math, and this time we're going to be moving functions across the x and y plane. And to do this, I decided to use a graphing program. In this case, I'm using Python, instead of writing things on the board, just because this is a neater presentation and a nicer display of the functions rather than me trying to manually draw these onto a whiteboard. And I'm going to be using the left-hand side of this to actually change the equation that's displayed here in the center, or to display the graphic, change the graphic that's displayed in the center. And on the left-hand side, you can ignore most of this. Really, I'm just going to be changing this line here. So as you can see right now, I'm graphing y equals x. So we're going to start off pretty simple right now. So y equals x. Let's move this function up by 3 units. To do that, we just add 3 to the right-hand side. And here I graph it. It moved it up 3 units. And I'm keeping this reference line here, this dotted orange line, as a reference, just to keep track of where we started. So now you can see we started at the origin, and the line moved up to now intersect y equals 3. And similarly, we can move it down 3 units by subtracting 3. And now you can see same line, same slope, but now it goes through -3. And this would work for any slopes. Right now I had a slope of 1, but we could do the same thing with slope of 3x. And in this case, I would have to change my reference line as well. But you can see moving it down, regardless of the slope, it still intersects, the intersection point is still changed by 3 units. So I'm going to change this back. Now what if we want to move it to the right or left instead of up or down? To illustrate how to do this, I'm actually going to change the function I'm using. So I'm going to use x squared, just because if we move a line up and down, it can look like it's moving left or right. So it's harder to tell the difference. So here I'm going to use x squared, which is a parabola. And in Python, to square something, you have to use this double times symbol, or use the times symbol twice, as opposed to a caret. That's just how Python works. So when you see this, just think, we're raising it to a power. So now we have our blue Python, or our blue parabola on top of our reference parabola, which is the orange dotted line. And we can see we can move it in the same way. So add 3, the parabola moves up. Subtract 3, it moves down. Now to move it to the right, what we're going to do is inside of the function, so inside the brackets, right now I have like x bracketed out and that raised to the power of 2. We have to subtract the distance we want to go. So now we're doing x minus 2 and squaring that entire thing, squaring all of x minus 2. And that's moved the function over 2 units. So now instead of crossing the origin, it crosses the x equals 2 line, or x equals 2 part of the x-axis. And you might be thinking, why are we subtracting 2 to move it to the right? It seems counterintuitive at first. You'd think you would be adding 2. But when you consider it, when you think, what do I have to do to get the y value to be 0 at x equals 2? And really, to do that, we have to subtract 2 from the x value so that we get 0 on the right-hand side. So we're really just trying to get back to 0. So whatever value of 2, however many units we move it over, we have to subtract that amount. And in the same way, if we want to move it to the right, we add a value. So I'll move it to the right 3 units, or sorry, to the left. If we want to move it to the left in the opposite direction, we have to add. So adding 3 inside, again inside the function, moves it to the left. And I'm using this with x squared. It works for really any function. For example, x cubed move x cubed to the left or right. I'll move x cubed to the right this time. And same thing. I could use a sine function or I could use a logarithmic function. It doesn't matter. Alright, now what if we want to flip this across the x-axis? We want to mirror it across the x-axis. So I'll sync up my reference and actual plots again. And to mirror it across the x-axis, all we have to do is make one of the sides negative. And there we go. We kind of flipped it over the x-axis and it's now a mirror image. And I'll go back. So again, just making it negative, flips it over. And now what if we want to flip it across the y-axis? So to do this, I'm actually going to shift it over to the left a little bit, or yeah, to the left a little bit, just so it's easier to see. Because if we mirrored it across the y-axis, since it's symmetrical as it is, you wouldn't really be able to tell that it was mirrored. Okay, so I'm going to keep the reference image there. Yeah, I just don't feel like changing it right now. So we're going to flip this over to the opposite side. To do that, we just have to subtract x, or make x negative. So now we have negative x plus 3 squared. Graph this. Boom, it's on the other side. So flipping it across the y-axis is done just by making the x term negative. And again, this would be the same if it was x cubed. So they're a different function, make it negative. And there it is mirrored. It's not just moving, it's actually mirrored across the y-axis. I'll go back to x squared. Alright, so we mirrored this function across the x-axis and the y-axis. What if we want to mirror it across a function, so y equals x? Mirror it across a straight line that's not perfectly flat or perfectly up. So to mirror it across the y equals x line, I'm going to change my reference line to be y equals x. To mirror it, we have to switch x and y, and then solve for y again. So I'm going to do this and talk through it at the same time on the screen. So here I just flipped x and y, so now I have x equals y plus 3 squared. Actually, before I do that, I'm going to copy and paste this just so I can flip back through real quick after I do this. Adding this little hash mark tells Python not to do anything with this line, so it kind of grays it out. Alright, so I'm going to flip y, or switch y and x, and solve for y. So first thing, switching y and x. And now we have y plus 3 squared on the right hand side. So to get rid of the square, we have to take the square root. So taking the square root of both sides. And to do the square root, I'm just raising to the power of 1/2 because those are the same thing. And now we have x to the 1/2 on the left hand side and y plus 3 on the right hand side. Get y by itself by subtracting 3. And now we have y equals x to the 1/2, or square root of x minus 3. And to graph this, I do have to put y in the left hand side. So we started from this top function here, switched x and y, solved for y, and we get this bottom function here. Alright, and I'm going to graph this on the screen, and you're going to see this parabola is going to jump over to this side but get mirrored to look something like this. And there we go. And Python's only going to graph just the top half in this case because mirroring the function will really make it no longer a function because it would have 2 values of y for each value of x, which isn't really allowed for functions. So it just graphs the top half. But now we can switch between these. So this was the original one, and you can see it's mirrored across this dotted line, y equals x. And now if we want to mirror it across y equals negative x, so I'm going to change, let's go back to the original function. And I'm going to change my reference line to now be y equals negative x. And I'll move my function over to the right, just so it's easier to see. There we go. So now it's on the right-hand side. I'm actually going to move it a little closer to the reference line. There we go. So now it's on the right-hand side, but pretty close to the reference line. So to mirror this across y equals negative x, we do the same thing we did last time. So we switch y and x, solve for y. But this time, we make the x value itself negative. And there we go. We flipped it across, oh, sorry, I still have this as -3. So there we go, -1. And now we flipped it across the y equals negative x axis, or mirrored it across that. So those are the basics of moving functions. We can move it up or down, left or right, or flip it across an axis or a straight line. I'm going to show you a couple examples of more complicated functions just to show you that these rules are still valid, and that'll really be all for the video this time. So let's do sine of x. So I'm going to get rid of these. To graph sine of x, because of the way Python works, I actually have to run it through a for loop here instead of the normal way I was doing it up top. So in this case, I have to use the math module to use sine. Again, don't worry about this. I'm just kind of talking about what I'm doing. But here, just imagine this as sine of x. I know it says sine of I, but just imagine it as sine of x. And we're going to graph this. And here we have a nice sine wave. And I'll change my my reference to be sine of x as well. And to do this, I have to do the same thing I did above. So sorry, I probably should have done this before. For in x, oops, it's going to be x2. Let's see, hopefully this works. Nope. I have to do math.sine. There we go. Okay, so now I have my reference on top of my actual line. So now we're going to move this sine function up 1 unit. And you can see all we have to do add 1 to the right-hand side. We can still move it down. We can move it to the right. Subtract 1. Oops, wrong button. There we go. We can move it to the left, so add 1. And we can mirror it. I'm not going to, well, I guess I'll mirror it. So mirroring it across the x-axis, we just make it negative. Mirroring it across the y-axis, we have to switch x and y. So in this case, I think arcsine is in the math module, but let's see. Nope, it is not in the math module. I forget what module it is. It's in, maybe it's in numpy or something. There we go. Okay, so it's in numpy. It's in a different module. But now I have arcsine or inverse sine, and Python's only going to graph the valid parts of this function, but you can imagine this continuing on up to the top and down, just oscillating in the same way. So it's mirrored across the line y equals x, as we'd expect. And I mean, we could do sine squared, and we'd see the same thing. So that's sine squared. Flip it to the opposite side, mirror it across the x-axis. We can move it up 3 units. And I apologize, I still have the original reference function on, so I'll take that off just so it's a little less annoying. But yeah, we can make this cosine. And let's see if there's anything else I wanted to do. We can also, I know I talked about absolute values before, but I can also show you a couple examples of absolute value with functions. So here we'll do cosine, and we'll see what happens when we take the absolute value of the entire function. So again, as a reminder, absolute value just makes any negative value positive. So in this graph, anything that's below the x-axis is going to be mirrored up to the top, but everything above the x-axis is going to remain the same. So taking the absolute value of the entire function makes this interesting little wave pattern that has a point. And we can make the entire thing negative after the absolute value and get a wave on the opposite side. So there's a lot of cool things you can do with some of these graphing programs to manipulate equations. If you don't know Python, you could also try this yourself on Wolfram Alpha, which is another pretty easy to use program. But I do like using Python just because there's so much stuff you can do with it.